Okay, so in the previous videos, I introduced you some two measures of variability based on percentiles. They were very intuitive and easy to calculate, easy to understand, so I introduced them first. And it was pretty simple idea. And now we are going to start from the very beginning again. What we are doing here is to define a measure of variability. And a measure of variability is to capture the distance from the center, right? So which is missing from a measure of central location. So to define a measure of variability, I'm going to define the center first. And of course, we are going to use the mean as the center. We are not going to question why the mean is the center. It's pretty like it's given, like take it as granted. So then given the center, we are interested in the difference between an observation and the center. So we may define deviation in this way. So deviation for an observation is, say, ith observation. Suppose you have n number of observations, then I can be any number between 1 and n. So deviation for one observation is simply the difference between the observation and the center, right? The mean. I'm going to call the mean as the center, like right for now. So this is defined as the deviation. So the observation is deviated from the center that much. It can be minus or it can be plus. So let's think about the weather example again. So let's take Honolulu and suppose that for simplicity you observe four observations on temperatures, one from each season, say spring, summer, fall, winter. And what you observe is simply, of course, again, the data are fake, made up numbers. So 76 in spring when you visited Honolulu in spring, and 82 when you visited in summer, and 80 when you visit in fall, and 74 in winter. So you have four observations of Honolulu's temperatures. So in this case, the mean is 78. I'm not going to show you how to calculate the mean. Should be simple enough, right? There are only four numbers, so I believe you can calculate the average of four numbers. And once you get the mean, that is the center. So center is 78. Then you may calculate the deviations this way. So in spring, you saw 76. That is 2 degrees below the center. So minus 2 is the deviation. And summer, it's 4 degrees above. And fall, 2 degrees above. And winter, 4 degrees below the center. So like when you define a deviation, you are measuring their location like relative to the center. Like minus 2 plus 4, it's relative to the center. So, and another thing another thing you need to note here is that because we have four observations, we can calculate four deviations. So there is one deviation defined for each observation, right? That is, if you had 100 observations, there would be 100 deviations. So I like to generalize your idea, you can think the deviations as a transformed random variable. So your original observations are temperatures, and you transform them into deviations by subtracting the mean. Then deviation itself is another random variable. We learned a transformation of random variable in the previous chapter. We are doing pretty much the same thing, right? It's another kind of transformation, right? Deviation, anyhow, we obtained deviations in this way. Nothing strange. But the problem here is deviations always sum to 0 because there are negative sides and positive sides at the same time, right? However, the sign does not matter. What we are interested in is the distance. Distance is what we are interested in. So there are many ways to remove the signs, but what we are going to do here is taking squares. If you take squares, then, for example, plus 4 and minus 4 will become equal. So plus 4 and minus 4 have the opposite directions, but basically they are from the same distance, like they are at the same distance from the center, right? So to capture this characteristics, this distance, we are going to square the deviations, and I'm going to call that squared deviation, right? Then it is another transformation, right? Original random variable is here, and transform once and another transformation, so we have squared deviations, and 4, which is minus 2 squared, 16, 4 squared, 4, 16. So 4, 16, 4, 16, which is a kind of distance because the further an observation is from the center, the larger the squared deviation is. And of course, you can define one squared deviation for each observation. So if you had 100 observations, there should be 100 squared deviations, right? So we are going to use this squared deviations as the distance. We may interpret this as a distance from the center for each observation, right? And then take this, just take the final random variable, final transformed random variable 416, 416, and take its average. Just take an average of this. That is what we learned in chapter 3. In chapter 3, we did some exercise of calculating transformation of a random variable and then taking average. We are doing the same thing here, just for a special purpose. Anyhow, so here we have the variance. The variance is the mean of the squared deviations. That's it. That is the definition of the variance. So what you need to understand is, you know what is the mean. Then you just need to understand what is the deviations. Squared, it's, you know what is a square. So if you know how to calculate the deviation, then just follow the definition. And it's intuitive. You know, deviation is deviation from the center. So take the difference. Mathematically, you can write it this way. So random variable x, and then its variance is written as VAR of x. Then its expected value of deviation squared. Squared deviation and take expectation, right? It takes kind of 3 steps. Deviation, square, expectation, right? And as I explained, it is like if you interpret square deviation as a distance, then you may interpret this as a kind of average distance. Average distance of observations from the mean, right? So the larger the variance is, the longer the distance from the center, so the more variation in the data, right? The data are more spread away from the mean. And because we took the square, all the square deviations must be non-negative. It cannot be a negative number. So square deviations must be always 0 or greater. So variance is always non-negative. If variance is 0, that is possible only when the random variable is a constant. It takes only one value with 100%. Then variance is 0. Later, we are going to denote the variance as sigma squared, Greek letter sigma squared, or lowercase letter s squared, s or sigma, right? To summarize, like I'm going to give you a formula for the variance, but here is a tricky thing. There are two different formulas commonly used in practice, and their names are population variance formula and sample variance formula. Excel has both. So that means Excel has a function means it is widely used, right? Already it has Excel has a built-in formula for these two formulas. Another problem here is that I'm going to explain them later, by the way. The name population and sample has nothing to do with the conceptual definition of population and sample. So from the very beginning of this course, I emphasized the difference between population and sample. Population variance, population is the ideal population is like observations of an infinite number of observations. Of course, it's not possible, but that's the truth. What we would like to know, right? That is the population. If you could observe an infinite number of observations, then you know the population. You know the population probability, population mean, population variance. On the other hand, you cannot observe infinite observations. So you only have a certain finite number of observations, which is called the sample. So it is just a part of the population, but we have it. We observe that. So you can calculate sample probability, sample mean, sample variance. If you calculate them from the data, we can call them sample object. This is more fundamental distinction of population and sample, the notion of population and sample. But the formula, the name of the formula has nothing to do with this idea. So let me explain. First, what's common is calculating the deviation, okay? Deviation and then square. This so far, calculating the squared deviation is the same for both formulas. And then you need to calculate the average, the mean, then sum and divide by the sample size. That's how you calculate the mean, the average. But sample variance formula divide the sum by n-1, not n. This is annoying. This is actually more common way to calculate the variance. This is annoying. For now, I just want you to take it as a formula. Later, I'm going to explain the reason why sample variance formula is different in chapter 8, because it is related to an estimation problem. Basically, we are kind of estimating the variance from the data. So this formula is derived as a result of estimation theory. So I'm going to explain it again later in chapter 8. For now, just practice, do some exercise depending on the formula. Like as before, earlier, we calculated square deviations this way. This was the square deviations, and if you use the population variance, you have to sum the square deviations and divide it by the sample size 4, which will give you 10. But if you use the sample variance formula, the denominator becomes 3, 4 minus 1. So the variance should be 13.33. That is the difference. But it's annoying, but I have no power to change it. Like in the homework, I'm going to give you what formula you have to use, right? So don't worry, and don't worry about what formula you need to use. But and in general, in practice, it does not matter that much. It does not matter that much. Like when the sample size is 4 and 3 is different a lot, like 33% difference. But if, for example, if your sample size is 1 billion, and 1 billion and 1 billion minus 1 does not make much difference. So as the sample size increases, the difference between these two formulas will get smaller. So I don't worry too much about it, but just use whatever you like. Sample variance is more commonly used, and I'm going to explain them again later, so choose what you like at that time. So summarize. When you have raw data, you calculate the variance following these steps. First, you have to calculate the mean first, which is the center. Fix the center first, and then subtract the mean from each observation to calculate the deviations. The first, that's so mean and then deviations, and then square the deviations, and then sum divide by n, right? But when you divide the sum by sample size, you may need to use n-1 if the formula is sample variance formula. So it is actually more involved and like more algebraically complicated, but not a big problem. Intuitive. So this is a practice. So now I gave you Phoenix data, the Phoenix data from Phoenix, Arizona, and try to calculate the sample variance. Sample variance formula. When I say calculate the sample variance, you calculate the variance using the sample variance formula. Hint, like to save your time, algebra. To save your algebra, I calculated the mean, which is 75. So do your exercise, and then if you finished, I will show you the answer. So we know the mean is 75. So deviations are -2, +20, +2, -20. So deviations squared, then 4, and 20 becomes 400. 20 squared, 20 times 20 becomes 400. So 400. And because we are using the sample variance, that is, the denominator should be 3. Then the variance in Phoenix is 269. So when you compare this variance with Honolulu, of course you have to compare it with the sample variance in Honolulu, not the population variance. So you have to fix the formula when you compare. Fixing the formula to the sample variance formula, it's Honolulu's variance is 13, but Phoenix has more than 260. Okay, like nearly 20 times, more than 20 times larger. Okay, this is it. I'm going to continue in the next video with another example. See you later.